Thank you for the introduction, Dr. Rowe. I'm just going to talk to you guys a little bit about the methods and results of our research, titled Arizona Butterflies Depend on Winter Rains. To begin, I'm just going to do a basic introduction to the methods we used and the models that we created. So for variable creation and selection, our main goal was to identify what effects the climate has on butterfly populations in Arizona. Some additional information about the data was some sites in the data set, including the preserve, sample multiple times a year. So to handle this, we created two groups. One we titled Spring, which is any samplings from March 1st to June 1st, and the second group being Fall, which is any samplings from July 15th to October 31st. Once we created these two groups, we had to create potential variables to analyze the data. Some of these examples are monsoon season precipitation, winter season precipitation, and previous 30, 90, 365 days above 30 degrees Celsius. Some other examples would be minimum temperature of the previous X amount of days, also max and mean. Once we created all the potential variables, we analyzed them and ended up going with these 7 variables. So the ones we selected were the sites themselves, year, so that as the study goes on, the minimum temperature in the previous 30 days, the maximum temperature in the previous 30 days, monsoon precipitation, winter precipitation, and party hours. So now that we have a little background about the models, let's just do a little comparison visually, so that way it's just a little easier for everyone to understand. Here's the site map showing the 13 different sample sites, just so you can get a little visualization of the diverse ecosystems in the data set. So right here in the middle, this octagon shape right here, this is the preserve. The octagon shape indicates that they sampled in the fall and spring, where over here you have Sycamore Creek and Boyce Thompson are triangles, so they're fall only. And up in the Grand Canyon area, there's some boxes that are only spring. Just to give a little background about the sites. So now that we've seen the sites, we're just going to move there. Talk a little bit about the overall precipitation throughout all the sites. On the x-axis, we have the year, and then on the y-axis, we have the precipitation total average for each site. So we have a 40-year time period from 1981 to 2021, and you can see right here, the blue line indicates the annual precipitation, the green with the winter, and the salmon color with the monsoon. The gray area around the lines is a 95% confidence interval. That means that we're 95% confident that this best fit line actually resides in this area. You can see that the monsoon precipitation doesn't necessarily change too much throughout the years. However, you see the winter with a decline causing the annual decline. And in these years, you can see some high points still here. As Dr. Rowe mentioned, in recent years, we've had some more rain. Now we're going to talk about overall party hours. So party hours is the time spent that the volunteers spend surveying in the field. Once again, on the x-axis, we have the 40-year time period, and on the y-axis, we have the party hours. As you can see, they are declining as well throughout the 40-year time period, and the confidence interval on the fall is much smaller than the spring. This is because in the fall we have 183 sampling events, whereas in the spring there's only 17. So we're less confident about all of the results in the spring just because the data set size.
Hey, Bradley, before
Yeah.
you go on too far into party hours, do you want to just tell folks what those mean?
Yeah, so that's the amount of time volunteers spend surveying on each sampling event. Sorry, I thought I mentioned that. Okay, so now that we've looked at the overall party hours, we're going to break it down by site. So here are the sites that we had. As you can see, the preserve is the second one. And on the y-axis, we have the party hours, which is individual or independent to each site. These are box and whisker plots. So the top part of the box and whisker plot indicates 75%. This little line here is the mean, and the bottom is 25%. And then the top of the whisker is 100, and the bottom is 0. Any dots would be outliers for this sampling set. as you can see, the preserve has a very small box and like no whisker, which indicates that they're very particular with their party hours. So they probably are around 15, 16 hours every time they go out. Whereas you have sites for like Patagonia that can vary anywhere from 55 to 70 party hours. So when looking at the spring, you'll notice that the preserve doesn't even have a box. And this is partially because of the small sample size. There's only 5 in the spring, so it's just started recently. And with the Grand Canyon sites, there's only 1 sampling for each of them, so they therefore can't create a plot off it. There's only 1 sampling. And then you have Sabino Canyon, which varies anywhere from 45 to 58-ish. Moving on from party hours, we have abundance. So once again, on the x-axis, we have each individual site. And then on the y-axis, we have the abundance. So this is the total number of butterflies that are sighted in each sampling event. So what you might notice that these follow a very similar pattern to the party hours. So the preserve itself is in the low to mid range and party hours. So it also stays in that way in the abundance. Whereas sites like Patagonia that had a lot of party hours also have a high abundance. The same trend can be noticed in the spring. The preserve itself had lower party hours than Sabino, and it also has a lot lower abundance. So now that we've looked at each site individually, this graph indicates the average of each site over the years. So on the x-axis is once again the 40-year time period, and then on the y-axis we have the average butterfly abundance of all sites for that year. These graphs look pretty steep, but they're really more visually like deceptive than what they really are indicating. So we have the fall in the pink and the blue is the spring. Once again, the confidence interval for the spring is a lot larger just due to the smaller sample size. So for the fall, annually there's a decline of 1.83% butterflies. This just means year over year there would be a 1.83% decline in butterfly abundance. There's also every 1 centimeter of monsoon precipitation increases abundance by 2.3%. So this means the fall abundance is really relying on monsoon precipitation. And then every party hour increases abundance by 3.56%. So this kind of ties back to the party hour graphs that we showed earlier, indicating how important party hours are. As we saw, they were decreasing over time. And that's really one of the main players in overall abundance decreasing over time. And then spring, there's a decrease of 9.35%. However, this number looks large and scary, but this is just once again due to the fact that there was only 17 samplings. So the time frame and the amount of samples wasn't necessarily large enough to give us a discrete value. And 1 centimeter of winter precipitation increases abundance by 4%. And every party hour increases abundance by 4.61%. So we can really start to see how party hours or time that volunteers spend out in the field surveying are playing a large role in this, which makes sense because the more exposure you have out, the more you're likely to see. Now that we've talked about abundance, we're going to start with site richness. So on the x-axis, we'll have the sites again, and y-axis, we'll have richness, indicating unique species seen in a surveying event. So once again, the preserve is towards the bottom, but this is also follows the same trend of the party hours, where you have sites such as Patagonia and Ramsey Canyon at the top, but if you remember, they were the 2 sites with the highest party hours as well. But then when we look at the spring graph, the preserve has a lot more variance in the unique species it sees compared to the abundance, where there was hardly even a box, it was just a line. And now Sabino Canyon has a lot less variance with their unique species compared to their abundance. So now, once again, looking at overall richness, similar to the overall abundance, we have the average butterfly richness on the y-axis, which is averaged out through the sites. And once again, these lines are pretty steep. But then when you look at the statistics, in the fall model, there's really a negligible decline in species richness annually. And there's also a negligible increase in species richness due to winter precipitation. And honestly, with the party hours, it's pretty small too. So every party hour the surveyors spend out in the field, they will increase the richness by 0.0015 species. If you're curious for these negligible, so this indicates one species every 47,000 years. So, and then it also indicates one new species every 34,000 centimeters of rain. Whereas with the spring, once again, the sampling size was smaller, but there's a richness decline of 2.16 species every year. And there's also every 2.31 centimeters of winter precipitation increases the richness by one species. So this is in showing you how important the precipitation totals are. And then every party hour increases richness by 0.76 species. So every additional hour that volunteers spend out surveying, they would see on average 0.76 more species. So now that we visually looked at them, I just want to kind of explain them again, or explain the results again. So as we talked, observer effort was a strong predictor for both butterfly richness and abundance. We saw in the graphs how they followed a similar pattern to the party hours. And this just means the more time observers spent in the field, the larger the values for both butterfly abundance and richness. And then when looking at the climate variables, precipitation had the largest effect on butterfly abundance and richness. It wasn't necessarily temperature as we originally may have thought. It was more so monsoon precipitation was the key precipitation on fall abundance, while winter precipitation was the important precipitation value for spring abundance and fall and spring richness. So when comparing our results to the initial Forrester paper that Dr. Rowe mentioned, they initially saw a 1.6 decline of the Southwest United States. Obviously, Arizona's in the Southwest United States, and we saw the 1.83% decline. So our results are pretty similar and aligned with what their findings saw. So now we're just going to talk about what does this mean moving forward. So the future, there's 3 main ways to maintain these butterfly populations. The first would be conservation measures. Breaking this down would be maintaining a large habitat patch size, maintaining the quality of natural areas, and maintaining corridors and natural connections among natural areas. A second key way to conserve these populations would be to minimize climate change. Any way we can, this allows for a larger adaptation period for these species, which gives them a higher chance of survival. And then the third way we can do is ensuring reserves. So any additional resources can help mitigate the effects of climate change and once again give them a increased survival rate. So that was all that we had. Dr. Rowe will now talk about the next steps of this experiment, and then we'll open it up to questions.
Okay. Oh. All right. So thank you, Bradley. That was great. We have tons of questions coming in the chat, but before we get to those, I just wanted to finish this up. I really wish I had a butterfly like Jesse had to show her way around, but I don't. But where this brings us is that we had our butterfly and we've been monitoring them. And then we took our results and we did some analysis. But there's further analysis that we want to do. So together with my collaborator, Dr. Broach, we would like to dig down into species level results to see if we can sort of pick out which species are sort of more in decline in our region. That can lead us to even more sort of management actions that we can think about for those species. So those are our next steps, and I want to open it up for questions. And so is somebody else going to monitor the chat and then ask questions to Bradley and us? And that was Doc.
Yeah, thank you, Helen, and thank you, Bradley. That was very informative. I think we have time for one question. I see one here was addressed in chat, but I'll relay it to you. It's how much data will be needed to separate short-term in other words, seasonal annual weather effects from long-term climate change effects.
Sorry.
Um,
So how much data would we need to separate short-term seasonal? So are you talking spring versus fall, or? Sorry,
Yeah, I
guess
think that
don't-
would be an example.
Okay, yeah, so as we talked, there was only 10 years in the spring and there was 40 years in the fall. So I think that would be a good measure, right around that 40-year mark. That's the same value that Forrester used. And then along with that, you would just get more samplings because we had 17 in the 10-year period.
And if you don't mind me butting in, there was a lot of talk about party hours and ways that we could think about that. But I do want to emphasize the fact that due to the fact that we had party hours in the model, it meant that we were able to separate that variation from what we were seeing in the overall decline by year and the decline that we could attribute to precipitation. And so because it was in the model, it's not necessary actually that everybody has the same party hours. By including it, we can sort of tell still what these trends mean. And so those trends that Bradley were showing, those are real, those percentages that were attributable to annual declines and to precipitation. Those are separated out from the party hours. So those still remain real butterfly declines, sadly.